5 part 3. Dear students, today we will discuss the third part of module 5. Okay, so module 5 part 3 starts with hard real-time systems. Hard real-time system. It is a real-time operating system which strictly adheres to the timing constraint for a task. Okay, a real-time system which strictly follows the timing constraint. The system response has to be obtained within the pre-allotted time. Okay, a hard real-time system must meet the deadlines for the task without any slippage. Missing any deadline may produce catastrophic results for hard real-time systems, including permanent data loss and non-recoverable damages to the system or users. It emphasizes on the principle a late answer is a wrong answer. Okay, so airbag control systems and anti-lock brake system ABS of vehicles are typical examples of hard real-time system, right? So they have to be operated within the time constraint, or else there is no use of having such systems in the automobiles, right? Like airbag control systems, anti-lock brake system, right? Within a stipulated amount of time, right, that particular system has to be operated. Otherwise there is no use of having such system. So they are highly dependent on the time. As a rule of thumb, hard real-time systems does not implement the virtual memory model for handling the memory. Okay, so there is no virtual memory model in case of hard real-time systems. So this eliminates the delay in swapping in and out the code corresponding to the task to and from the primary memory. So because of absence of this much virtual memory concept, there is no swapping in and out of the code uh, uh, corresponding to the task to and from the primary memory. So directly we have primary memory there. So there is no concept of having virtual memory. So there is no swapping between the virtual and the primary memory taking place in case of hard real time system. The presence of human in the loop, that is HITL, human in the loop, for task introduces an unexpected delays in the task execution. Okay, presence of human in the loop for task introduces unexpected delays in the task execution. So most of the hard real-time systems are automatic and does not contain a human in the loop. So the other category is soft real-time operating systems. Okay, the real-time systems that does not guarantee meeting deadlines but offer the best effort to meet the deadline are called as soft real-time systems. Missing deadline for tasks are acceptable if the frequency of deadline missing is within the compliance limit of the quality of service. Okay, so missing deadline for task is acceptable if the frequency of deadline missing is within the compliance limit of the quality of the service. A soft real-time system emphasizes on the principle a late answer is an acceptable answer, but it could have been done better. Okay, so, or a bit faster. A late answer is an acceptable answer, but it could have been done bit faster. Okay, so that is the principle of operation in case of soft real-time operating systems. Soft real-time systems most often have a human in the loop. Okay, so the soft real-time systems will have human in the loop. Automatic teller machine is a typical example of soft real-time system. If the ATM takes a few seconds more than the ideal operation time, nothing fatal happens, right? That is why this comes under soft real-time systems. So some amount of delay is acceptable and nothing fatal will happen if the response is delayed by some time. Okay, an audio video playback system is another example of soft real-time systems. No potential damage arises if a sample comes late by a fraction of a second for a playback. Now in operating system we often hear about these terminologies: task, processes, threads. We'll see what are those. Okay. In the operating system context, a task is defined as the program in execution and the related information maintained by the operating system for the program. Okay. Task is defined as the program in execution and the related information maintained by the operating system for the program. Task is also known as job in the operating system context. A program or part of it in execution is also called a process. Okay. So the terms task, job, process refer to the same entity in the operating system context, and most often they are used interchangeably. Okay. The process requires various system resources like CPU for executing the process, memory for storing the code corresponding to the process, and associated variables and I/O devices for information exchange, etc. So we will see the structure of a process. Okay. The concept of process leads to the concurrent execution of tasks and thereby the efficient utilization of the CPU and other system resources. Okay. So process leads to concurrent execution or parallel execution of the task. Okay. So which helps in efficient utilization of the system resources such as CPU, memory, buses. Okay. So these are the system resources. Concurrent execution is achieved through the sharing of CPU among the processes. Okay. So the process mimics a processor in properties and holds a set of registers. Okay. A process mimics a processor in properties and holds a set of registers: process status, a program counter to point to the next executable instruction of the process, a stack for holding the local variables associated with the process, and the code corresponding to the process. Okay. So the process also holds some of the registers to mimic the actual processor. Those are the process status register, program counter register, stack pointer register. Okay. And some working registers. A process which inherits all the properties of the CPU can be considered as a virtual processor, awaiting its turn to have its properties switched into the physical processor. When the process gets its turn, its registers and program counter register becomes mapped to the physical registers of the CPU. Okay. When the process gets its turn for the execution by the processor, its registers will be mapped to the actual physical registers of CPU. Okay. In the figure we can see the registers which are utilized by the process, and then when the process gets its turn to get executed, these registers are converted into actual processor registers. Memory organization of a process. Okay. So the memory occupied by the process is segregated into three regions, namely stack memory, data memory, and code memory. The stack memory holds all temporary data such as variables local to the process. Right? Stack memory is usually used to hold the temporary data such as variables which are local to the process. Data memory holds all global data for the process. Okay. The code memory contains the program code or instructions corresponding to the process. On loading a process into the main memory, a specific area of memory is allocated for the process. Okay. When the process is loaded into main memory, a specific area of memory is allocated for the process. Okay. So process, as you know, process means a program which is currently under execution. Okay. The stack memory usually starts at the highest memory address from the memory area allocated for the process, okay, depending upon the OS kernel implementation. So you know that stack memory is always the top part of the memory, because stack memory always grows downwards, right? The stack pointer is decremented each time, and then in the decremented location the data is stored. So the stack memory grows downwards, whereas data memory or the code memory grows upwards. That is what is shown in the figure. So then we have process states and state transition. What are the different states of the process inception and its execution and the completion of the execution? Okay, so the creation of a process to its termination is not a single step operation. The process traverses through a series of states during its transition from the newly created state to the terminated state. Okay, process traverses through a series of states during its transition from newly created state to the terminated state. The cycle through which a process changes its states from newly created to execution completed is known as process life cycle. So process life cycle starts from newly created and ends at execution completed. The various states through which a process traverses through during a process life cycle indicates the current status of the process with respect to time, and also provides information on what it is allowed to do next. Okay, the various states through which a process traverses during a process life cycle indicates the current status of the process with respect to the time, and also provides information on what is allowed to do next. So this information will be available through the process life cycle. So here there is a figure of a process life cycle indicating different states of a process. Okay, initially process creation or inception, then process ready state. Okay, so it is created means it is incepted into the memory, and then a ready state. From ready it will go to the running state. Okay, so through the scheduler for execution. Okay, from running phase there is a chance to go back to the ready state if it is interrupted or preempted. Okay, if the process is interrupted when it is under execution, it will go back to the ready state, and when it is scheduled for the execution, it will come back to the running state. Okay, running means execution of the process. Okay, so ready means it is waiting for the resources like CPU, bus and memory and so on. Okay, so from the running state, that is the execution state, the next state is completed state, the completion of the execution. Okay, execution completed. Now in the running state or from the running state, there is a chance that it will go to the blocked state if it is waiting for the IO resources. Okay, and from the blocked state it will go back to the ready state once again if IO allocation is done, input output resources are allocated. It will go to the ready state, and then from ready state again it will go to the running state. Okay, if it is scheduled for execution, and from the running to the completed state if the execution is completed. So this is a process life cycle which shows different states of, okay, the life cycle starting from the creation till the execution completion. Brief explanation of each state in case of process life cycle. Okay, process states and state transitions. So first we had created state. A state at which a process is being created is referred as created state. The operating system recognizes a process in the created state, but no resources are allocated to the process. Then we had ready state, the state where A process is incepted into the memory and awaiting the processor time for execution, known as ready state. Okay, the process is incepted into the memory and waiting for the processor time for execution, so that is ready state. At this stage, a process is placed in the ready list queue maintained by the operating system. Okay, so the process is placed in the queue that is called as ready list, okay, which is maintained by the operating system. Then running state, a state where the source code instructions corresponding to the process is being executed, is called running state. Running state is the state at which the process execution happens. Okay, then we had blocked state or wait state, which refers to a state where a running process is temporarily suspended from execution and does not have immediate access to resources. The blocked state might have invoked by various conditions, like the process enters a wait state for an event to occur. Okay, for example, waiting for user inputs such as keyboard input, or waiting for getting access to a shared resource like semaphore, mutex, etc. So we already discussed about semaphore and mutex in the last presentation. Okay, so this is about blocked state or wait state. Okay, which refers to state where running process is temporarily suspended from execution and does not have immediate access to resources. Then the completed state, a state where the process completes its execution. Okay, completed state means a state where the process completes its execution. The transition of a process from one state to the another is known as state transition. Okay, and then when the process changes its state from ready to running, or from running to blocked or terminated, or from blocked to running, the CPU allocation for the process may also change. Okay, so when there is a state transition from ready to running, or from running to the blocked state, or from blocked to the running state, the CPU allocation for the process may also change. Now we will discuss about threads. Okay, a thread is a primitive unit that can execute code. Okay, so primitive unit means the basic unit which can execute code. Okay, a thread is a single sequential flow of control within a process. Okay, so thread is an actually execution unit which consists of its own program counter, stack and set of registers. Okay, and thread is also known as lightweight process, a process that can have many threads of execution. Okay, process can have many threads of execution. Different threads which are part of a process share the same address space, meaning they share the data memory, code memory and heap memory area. Threads maintain their own thread status, that is CPU register values, program counter and stack, as well as stack pointer. Okay, so every thread will have its own program counter, stack pointer and the status registers. Okay, so a process can have multiple threads. Now what is a process? Process is a program under execution, and it can have multiple threads, where thread is a basic unit that can execute a code. Okay, a thread is a single sequential flow of control within a process. So there can be many independent threads. So different threads share a common data memory and the code memory, but every thread can have its own program counter, status registers and stack pointer. Okay, so be very careful between the difference between the process and the thread. We studied about the process till now, and now in this slide we are studying about the thread. Okay, so process is a program under execution, and it can have multiple threads, and it can have parallel processing of the threads, or the parallel processing is possible by having multiple threads and these threads will have all these threads will have a common data and the code memory, but every thread can have its own program counter stack pointer. So thread is a sequential flow of control, okay, within a process, where the process means the program under execution. So in this figure you can see a data memory for process, code memory for process, and then as I told you, a single process can have multiple threads, and all these threads will share all these threads will share the data and the code memory. So data memory and the code memory is common for all the threads under each process, okay. So we have two threads shown here. So this is the stack memory for thread 1, this is the stack memory for thread 2. So every thread will have its own stack memory as well as program counter as well as status registers, whereas all the threads will share a data memory and the code memory, okay. So data memory and code memory is common for process, and a process will have multiple threads. So I am repeating it so many times, okay, don't get confused between the process and the threads. So this figure shows you a clear picture, okay, or it will give you a clear difference between process and the thread. So this is a task or the process, which is a program under execution, and every process will have a code memory and the data memory, which is common for all the threads, okay, under it. So we have thread 1, thread 2, thread 3. Each thread have its own status registers and the stack pointer, okay, stack pointers and the status registers. And what is thread? Thread is nothing but a sequential control of the program. So we have already seen there were multiple threads under each process. So what are the advantages of these multiple threads? The concept of multi-threading. Use of multiple threads to execute a process brings the following advantage: better memory utilization, okay, multiple threads of the same process share the address space for data memory, right. This also reduces the complexity of inter-thread communication, since variables can be shared across the threads, right. Having the common data memory has the better memory utilization advantage, right, because the different threads share the same data memory, so the communication between the threads is reduced. Since the process is split into different threads, when one thread enters a wait state, the CPU can be utilized by other threads of the process that do not require the event which the other thread is waiting, okay, for processing. This speeds up the execution of the process, okay. So we have seen a single process is executed with the help of multiple threads. So what is the advantages of having this multi-threading or parallel threading, okay. So if one event does not require a CPU, and then the other threads can make use of the CPU, okay, yeah, CPU utilization can be done by the other threads when one thread process is in the wait state. So CPU time is utilized efficiently, it is not wasted, okay. So efficient CPU utilization, the CPU is engaged all the time. So this is the advantage of multi-threading or parallel threading, which is also the case of a normal parallel or multitasking operation. So thread standards. Thread standards deal with the different standards available for thread creation and management. These standards are utilized by the operating systems for thread creation and thread management. It is a set of thread class libraries. The commonly available thread class libraries are POSIX threads. POSIX stands for Portable Operating System Interface. The POSIX.4 standard deals with the real-time extension, and POSIX.4a standard deals with thread extension. The POSIX standard library for thread creation and management is pthreads. Pthreads library defines the set of POSIX thread creation and management function in C language. Win32 threads. Win32 threads are the threads supported by various flavors of Windows operating systems. The Win32 application programming interface libraries provide the standard set of Win32 thread creation and management functions. Win32 threads are created with the API. Java threads. Java threads are the threads supported by Java programming language. The Java thread class, okay, thread is defined in package java.lang. This package needs to be imported for using the thread creation function supported by the Java thread class. There are two ways of creating threads in Java, either by extending the basic thread class or by implementing an interface. Extending the thread class allows inheriting the methods and variables of the parent class, that is thread class, only whereas interface allows a way to achieve the requirements for a set of classes. Thank you.